بالظبط عشان ما تقلبش معانا منه. لا انا بس لا اصلا ما خلاص طلع كده هم التفاصيل ولا معي ولا مع ولا مع حالك. شو انت اليوم بتحكي بقى خلاص يلا شوف كل يوم ايه تكمل في بدك تخلصه مش تخلصه اليوم هو اللي بعد خلص لا أحسن عليك هو بعد ما يروح مش بعد So are we lecturing them?
Yes. Yeah, lecture today, activity on Thursday.
What? That's right. Even though you're yeah, because I also did that. Shared it to myself first. Well, I did it on myself on my email, and then I sent it. Yeah.
السؤال السادس السؤال السابع السؤال الثامن عبارة عن
Oh my goodness, you didn't put that video. I saw that in the beginning, and I was like, no, it has nothing.
كل كفر
Huh? No, I
So the best is
That's the maximum. Yes. So for normal material, yes, but because the material we're using against this is isotropic, then there's no difference between tensile. So it just looks at just the value. Yeah, so for normal material, yes, compression, normally material is compression. Because the difference, but because we're using such a simple material model, we use certain expenses.
Yeah. You said this is and church. Oh.
الشكل هذا كيف انا وصلت هذه تعرفوا كيف هذا
Other had a homework. For today, it's good. That's probably long. This week. I think I'm gonna have a quiz. Thursday. It's not hard, but it's like you have to study for it. Because I forgot most of the differential equations, like derivatives, integrals. I completely forgot about it. So
Okay, so it seems like it's all the same. Then.
what else after this class? Yeah.
Is that 8 tomorrow? 7, no 7. That just sucks.
Yeah, I know. Just come for that class, right?
Yeah, so I just do it. You know.
And everything. So that's how I think so. This I was like, yeah.
I'm
There's nothing.
starting to like study.
It's a big portion, right?
All the sections. For the children. The section for the math class is really short. I think it's about like. I had a. Maybe just another class. That's pretty chill. So I think I'm gonna get a good grade.
Like it was like.
Conversion stuff. That's what I've been doing because I saw nothing.
Enjoying it. Not really. I have to see it and getting easier and after like doing it once.
I was like, I want to hear.
ما بعرف
You know, yeah.
انا مشيت يعني ما بعرف
Like,
عن صفة تعرف
yeah.
مش متأكد عليه
That's smart.
سيريا انا معروف عن السورية معاك
Oh, you said you're ready.
معكش كتير معاك معروف
Cool.
ده كيف مثلا فلسطينيين
Great to feel that word. Readable best.
مش مشكلة بالعكس
All right, 5:30, let's go and get started. Right, good evening, everyone. How's everyone doing today? Good to hear. Yeah, I didn't know that the university was observing President's Day on Friday, so I worked on Friday. And then I found out that I was supposed to work yesterday because the holiday was on Friday, so I didn't get a long weekend, just worked the whole time, so. Okay, all right, so today, so this week is exciting, so we have another ANSYS activity this week, so that's what we're gonna be doing on Thursday. Remember Thursday, we're gonna have to cut our lecture a little bit short because the school is doing an evacuation drill. So we're gonna be ending our lecture at 6:30 on Thursday, so as of today, I still remember. But if I'm panicked because the siren started blaring at 6:30, just remind me that this is happening. So today we're gonna have another lecture. So we're pretty much done with all of the, I would say, the very basics of the basics of FEA. We went over meshing, boundary conditions, material properties, as well as, remember we did some background information about just material, strength of materials in general. So now we're going to start to get into kind of a little bit more advanced stuff. And so we're returning to meshing right now. And we're talking a bit more, we're going to give a bit more context between or behind all the different meshing properties, all the different meshing, settings that you can do, starting with element order. So we're going to be spending a lot of time on that today, talking more about what that means and kind of the different options that you have available for the. Okay. All right. Are there any questions I can answer before we get started for today? Okay. All right. So let's go and get started. All right. So before we kind of dive back into talking about the different types of elements and different element settings, we have to go over kind of an important concept in finite element meshing, which is the idea of the shape function. So the shape function is kind of a core feature of the finite elements that really determines basically all of their behavior in terms of how things are solved. Okay, so let me just start by just reminding you that finite elements, as powerful as it is, at the end of the day, it's just a method for solving partial differential equations. Okay, in particular, FEA is just we're finding approximate solutions to these partial differential equations. Okay. So the way FEA works is that you have your geometry, it's defined by a CAD model most likely, and you want to solve the governing differential equations based on your structural mechanics, heat transfer, fluid mechanics, whatever equation you're trying to solve. You're solving the differential equations and you're finding an approximate solution to those partial differential equations. Okay. So let's kind of dive a bit more into what I mean by approximate solution. Okay, most of the time, when you're given a math equation to solve, you solve the equation, I would say, kind of directly. Right? And so that means that, you look at the equation, you apply some kind of technique or some kind of algorithm to solve the equation, and you get your solution, right? The way I like to describe it is, you kind of solve straight from the equation itself. Okay. And then based on your solution technique, whatever form or whatever your solution looks like, that's just kind of what it looks like based on the equation. Right, so if you think back, to our lecture on boundary conditions, there was that time when we solved that differential equation, right? And so, when we solved that differential equation, we didn't make any assumptions on what the solution would look like beforehand. We just solved the equation, and then whatever the solution ended up being, that's just what the solution was. Okay. So this technique, or this way of solving equations is, I call it kind of a direct solution, direct exact solution. Oftentimes, this method doesn't rely on any kind of assumptions or any kind of, fancy tricks. You just solve the equation straight up and you get your solution, and that solution is exact, right? And so by exact, what I mean is that, it satisfies the equations perfectly. So there's no approximation. Okay. Okay. So I bring this up, because this is something that finite elements does not do. So finite elements does not find an exact solution, it finds an approximate solution. An approximate solution, just you can tell by the name, is less accurate than exact, and so there's going to be some discrepancies with the exact solution. Right, so that's it. Just in its nature, an approximate solution is never going to be as accurate as the exact solution. But oftentimes, if you're careful in how you form the approximate solution, how you kind of obtain it, you can minimize those errors to basically a negligible amount. And so with proper technique, you can find an approximate solution that closely mirrors the exact solution. So finding approximate solutions is not something that's unique to FEA. There are a lot of techniques in engineering and applied math and in science that do find approximate solutions, right? Usually the benefit, or usually the appeal of finding an approximate solution is that it's usually a lot easier to obtain than the exact solution, right? Especially for very complicated cases. really, you can only really find direct exact solutions for kind of the simplest of cases. So simplest equations, simplest geometries, oftentimes you can really only do it in 1D. You can find exact solutions in some 2D cases, some very select 3D cases, but if you have any kind of complexity, it really kind of becomes practically impossible to find an exact solution. So you're kind of limited to just approximate what's there. And that's kind of where FEA kind of excels, is to find these approximate solutions in a very easy manner that you can do in a computer. Okay. Okay. And again, finding approximate solutions is not unique to FEA. It's just FEA is just one form of this. Okay. So what does FEA do that's unique? So how does FEA actually find an approximate solution? So the way FEA finds an approximate solution is by assuming a form of the equation or assuming a form of the solution before you even start. And so in some ways, in this way, it's kind of the exact opposite of finding a direct solution, because for a direct solution, you just solve the equation and just whatever form it takes, that's the form it takes. For FEA, a big part of it is making an assumption beforehand that your solution is going to take a certain form. And then from there, you basically then plug in that assumed form into the equations and find the best function of that form that satisfies your equation. So in particular, for FEA, we usually are looking for polynomial type solutions, so linear functions, quadratic functions. Those are the types of functions that we solve for. So, this idea, we did touch on this briefly before when we talked about meshing. So this idea of choosing a polynomial order or choosing a polynomial function to represent your solution before beginning, remember, this has to do with the order of the. So remember, there's kind of two primary choices when you're choosing element order for your finite element mesh. You can either choose a linear element or a quadratic. Okay. So that's kind of what we've kind of discussed before. So this was kind of just a review of that. It turns out that every single element has something called a shape function, which is exactly that, which is the shape function is a polynomial with the exact order that we specified, from the beginning. And so the purpose of the shape function is, you know, basically what's used by the element to approximate the solution to the governing differential equation. Well, one thing that we didn't really discuss last time is that the shape function actually takes a different form depending on the shape of the element as well. So the exact shape function depends, first of all, on the order of the element. And so that's going to tell you whether you have a linear or quadratic shape function. But the number of terms also change based on the shape of the element as well. So later on today, we're going to go through all the different 2D element types. And so we're going to go through triangles and quadrilaterals, both the linear and quadratic versions of them. And we're going to show exactly what their shape function looks like. Okay. All right, any questions on anything we've discussed so far? Okay, good. All right, so let's start our discussion with you know, talking about how do we actually, you know, or what do these shape functions actually look like. So let's start with the simplest element that we can imagine in 2D, which is a linear triangular element. Okay, so just like the name implies, the triangular element will look like a triangle. Okay, let's go ahead and draw that first. So our triangular element will have 3 nodes. 1, node 2, node 3. Okay. And because it's linear, then our shape function is going to be a linear function as well. Okay. But remember, we're in 2 dimensions here. And so we have to have linear terms both in X and in Y as well. Okay. So the symbol that I'm going to use for shape function is I'm going to use a capital T. And our shape function in this case is going to be a function of X and Y. Okay. So let's go ahead and fill in what this shape function is going to look like. So for a linear function, that means we're going to have functions that are both linear in X, linear in Y. But we actually also have to include all of the lower order terms as well. So the only term that's lower order than linear is a constant term. And so we're going to have A0. A0 there is going to represent our constant term. We have A1 times X and A2 times Y. So we have our constant term and linear terms in both X and Y. Okay. So you can see kind of all terms of the linear polynomial kind of represented in this function. Okay, where A0, A1, and A2, these are all constants. And as of now, their values are still undetermined. But they're just constants. And so, you know, they're just going to have a single value for that particular element. Okay. So this is the shape function for a linear triangle, right? It's important to remember that every single element in your mesh will have its own shape function. So all the shape functions for all the elements are going to have this same form. So what's different between the different shape functions of the different elements is the values of these constants. Okay, so even though every element in your mesh may be a linear triangle, right? All of the shape functions are going to look slightly different because of the values of those constants, right? So let's talk about those coefficients. And so how do we actually determine those coefficients? Well, in this function here, they're arbitrary, but there has to be a way to solve for their values. So the values of the coefficients are determined based on what I call the nodal solutions. Because even though every single element has its own shape function, right? The solution to the FEA has to be consistent when you go from one element to the next, right? And the nodes are something that's shared between a lot of neighboring elements. Right? Okay. And so if you look at kind of a typical mesh, here we have kind of 4 elements, A, B, C, and D. All of them share that one node that's kind of in that middle. So each of those elements, elements A, B, C, and D, they're all going to have their own shape functions. But ideally, they should all get the same value of the solution at that node. Okay. And that's needed just for a consistent solution. Okay. So the way you do this is basically when you're looking at an individual element, right? The way that you solve for the constants in the shape function is to make sure your solution matches the nodal solutions. Okay. Let me kind of illustrate what that means. So for a linear triangle, Your triangle looks something like this. 1, 2, and 3. Okay. So just for the sake of simplicity, we're going to be looking at a heat transfer situation here. And so the solution that we're going to solve for is temperature. Okay. The reason I'm doing this is because for a structural simulation, static structural, we solve for the deformation of the nodes, and deformation is a vector-based quantity, so it has x, y, and z components. Right? For heat transfer, temperature is just a scalar quantity, so it just has one value. Okay, so for every node here, we're going to have a value of the temperature. We have T1, 2, T3. Okay. So those are the solutions that have to match, and so our shape function has to achieve those values at those nodes. Okay. And at every node here, we also have their spatial coordinates. We have x1, y1, x2, 2, 3, y3. Okay. So for every node in our element here, we not only know what the solution should be. Okay, so we know what the nodal solution should be. That's T1, T2, T3. We also know their spatial coordinates. Okay. And so this is going to give us the basis to solve for our 3 unknowns, because what we can do is we can set up a system of 3 equations. Okay. Where basically we're going to enforce that our shape function matches the nodal solution when we evaluate them at each node in this element. Okay. So basically when we evaluate t at x1, y1, okay, it's going to equal t1. This is equal to 0 plus a1 x1 plus a2 y1. And then when we evaluate t at x2, y2, it's going to be equal to t2, which is equal to a0 plus a1 x2 plus a2 y2. T at x3, y3, 2, t3, 2, 0 plus a1 x3 plus a2 y. All right, and so by enforcing that our shape function matches all these nodal solutions, we have 3 equations which are going to allow us to solve for each of the unknowns, a0, a1, a2. Any questions on this so far? Okay. Great. So this is the requirement that the shape function should hold. So basically what's happening underneath the hood when you solve your ANSYS equation is ANSYS is solving for each of these constants for each of the elements in your mesh to make sure that your solution matches up at the nodes in the mesh. Okay. In fact, if you were curious, ANSYS kind of does this simultaneously for all of the elements in the mesh, right? And then it uses that together with the governing equations to first basically solve for all the nodal solutions. Okay. Nodal solutions in FEA simulation T1, T2, T3, and in a structural simulation, this will be deformation X, Y, Z at each of the nodes. So DX1, DX2, DX3, DY1, DY2, DY3. Okay. Nodal solutions kind of serve as the focal point for all your finite element mesh, and then based on those nodal solutions, the solution everywhere else is determined based on the shape function of the element. Okay. So when you're looking at the mesh and you see kind of the number of nodes in the mesh, the number of nodes does actually play a role. Because a lot of times when we're talking about FEA, a lot of times we talk specifically about the number of elements. And in a lot of ways, the number of elements determines the cost because that's basically how many shape functions that you're going to have. That's a number of shape functions that you're going to have to solve for. But the nodal solutions actually do play a very important role as well. So it's important to kind of keep track of that as well. Okay. Okay, but another thing that this kind of example highlights is the connection between, first of all, the number of nodes that we have in the element and the number of terms in our shape function. There's a connection in the fact that they have to be the same. So the number of nodes in your element equals the number of terms in the shape function. Okay, so we just went over kind of the simplest shape function that we have, which is the linear triangle. So let's step it up one level. So let's look at the linear quadrilateral. Okay, so the linear quadrilateral element, this is kind of like the two-dimensional version of a hexahedron, right? So a quadrilateral has 4 sides and 4 nodes. Okay. One, two, three. By the way, the ordering of the node numbers doesn't really matter. That's just how the way I do it. My mind thinks counterclockwise because I'm indoctrinated by the right-hand rule, I guess you could say. Okay. The most important thing is that there's 4 nodes, right? And so because there are 4 nodes, that means our shape function has to have 4 terms. Right? So we have to basically have 4 unknown constants because we have 4 nodal solutions to match. Okay, it has to have 4 terms, but it must be a linear function at the end of the day too. And you're going to see we're actually going to run into a little bit of a conundrum with that. Okay, so let's look at what the shape function looks like here. So we have t x comma y. Okay. So we need 4 terms and we need them all to be linearly independent from each other. And it needs to be linear. So there's kind of a strict requirement here. So just like we did with the linear triangle, let's start with the constant terms. We have a0. We have a constant term because we need it for our shape function. Next, let's consider the linear term. So we have a1 x plus a2 times y. Okay. So that's good. So we have 3 terms down. In fact, these are the 3 terms that are in our linear triangle as well. Okay, but we need one more. And we can't really repeat any of the terms that we have so far. So if we repeat the terms, then they're going to be linearly dependent on each other, and they're not going to form a complete set. Okay, so we need one more linear term, but we're going to kind of cheat a little bit because there's no more linear terms that we can add, but we can add what's called a pseudo linear term. Okay, so our 4th term in this expression is going to be a4 x times So of course, you might be looking at that and be like, wait a minute, that's not a linear term. That's one variable multiplied by another. That's a quadratic term. And you're right, technically speaking, this is not a strictly linear term because you have two independent variables multiplied by each other, x times y. But individually in x and individually in y, this term is technically linear if you hold the other. So that's why oftentimes we call this term the pseudo linear. Technically not linear, but linear in each of the dimensions one at a time. And this trend is going to continue. So when we get to the 3D elements, you're going to have pseudo linear terms there as well. Okay. And so just like we did before, we can solve for the values of these four constants by matching the nodal solutions. So for each of these corners here, we have T1, T2, T3, T4, as well as its physical coordinates. So x1, y1, x2, y2, x3, y3, x4, y. And so to solve for the four constants, we have a0 plus a1 x1 plus a2 y1 plus a3 x1 y1. This has to be equal to T1. And for the second equation, we have a0 plus a1 x2 plus a2 y2 plus a3 x2 y2 is equal to T2. Third equation, we have a0 plus a1 x3 plus a2 y3 plus a3 x3 y3 equal to T3. Finally, a0 plus a1 x4 plus a2 y4 plus a3 x4 y4 equal to It's a small miracle. I did not make any mistakes on the sub indices there. I did double check and make sure that I didn't make any mistakes because I almost always make a mistake with this set of equations here. All right, so what we have here is a set of linear equations, four unknowns, a0, a1, a2, a3. So we can solve these four equations simultaneously for those values. Okay. Of course, I'm not going to do it here. That would be kind of crazy to do. Probably take us into the end of class. But in theory, the solution exists, and this is something that you can solve for, in a computer much more easily. Okay. Good. All right, so the linear quadrilateral is interesting, mostly because of the presence of that pseudo linear term. So if you think about, besides the shape of the element itself, if you compare this element to the linear triangle, the presence of that pseudo linear term is really kind of what separates this from the linear triangle, and it actually makes a big difference. Remember, when we first we kind of first introduced some basic concepts of the mesh, we talked about generally the rectangular elements are superior to the triangular elements if you can get them to mesh. So that was something that we mentioned before, but we didn't really talk about why that was, right? So part of the reason why rectangular elements give you a better quality solution than triangular elements is that in general, rectangular elements have more terms in their shape function than the triangular elements. And so for the linear, for the linear elements, it's only just one additional term, but that one additional term actually makes a big difference. Okay. Remember, because the shape function represents what your, it represents the form of your approximate solution, right? And so the more terms that you have in your shape function, the more types of behavior your approximate solution will be able to model in the final solution. Okay. And so when we compare, so when you compare the shape function for a linear triangle and the shape function for a linear quadrilateral, having that extra term there means that there's more types of solution behaviors that you can actually model. So let's look at both shape functions kind of side by side. So if we look at the linear triangle. So for the linear triangle, our shape function t of x, y is equal to a0 plus a1x plus a1y. Okay. So what types of behaviors or what types of solution behaviors are we able to model with this type of shape function here? So, we can model, constants, okay? That's basically going to be any constant offsets or constant biases in your solution. That is our A0 term, right? So the A0 term takes care of any biases in our solution. Okay. And then we're also able to model, or we're able to capture any solution behaviors that vary linearly in X and linearly in Y individually. Question, yes.
Should it be in A2 for the second?
Oh, yes, thank you. I was bragging earlier about making the subsets correct, and of course I make one wrong. I deserve that for bragging. A1 and A2. Okay, so it's pretty limited, right? And so this is not a lot of behavior that you can find. Okay. And so when we compare this to the linear quadrilateral, linear quadrilateral has those same terms, except it has that cross term as well. So we have t of xy is equal to a0 plus a1x plus a2y plus a3xy. So you can see here for the linear quadrilateral, we can do everything that the linear triangle does, right? So points 1 and 2 here are also the same. Except we can also model behavior that depends on X, Y. So things that have both X and Y dependence at the same time. That's our brand new kind of A3 term. All right. And so, because there are kind of more degrees of freedom and kind of more kind of terms in our shape function for the quadrilateral, this most of the time leads to a better quality solution, a more accurate solution, one that more closely resembles the exact solution. Okay, so having more terms in your shape function is generally a good thing. That just means that you're able to capture more behavior. Right? And so that's why kind of the linear quadrilateral, that's why we say that rectangular elements generally lead to better quality solutions, just so they just have more nodes in their element compared to all right. Any questions on this? Okay, good. Another really interesting aspect and so this is kind of more specific to just the linear elements, is that the linear quadrilateral has the very special property where its derivatives are non-constant. Okay, or maybe I should say the reverse. And so when you take the derivative of the shape function of the linear triangle, you're always going to get a constant function at the best case. So let's say that you take the partial derivative of your shape function with respect to x, and so that's going to give you a1, right? So partial t x, a1, okay? A partial t partial y, you end up with a2, okay? So because your linear triangular element is limited to just a pure linear function, taking its derivatives is always going to lead to a constant, which is it's great for simplicity. And so when you're deriving these finite element equations, or when you're kind of writing your own code, this is great because it cuts down the amount of code that we have to write. But in terms of solution quality, this is actually not that preferable. Because what this means is that any quantity or any solution that depends on the derivative of your primary solution, it means that it's going to be under approximate. Okay. And there are a lot of quantities of interest that do depend on the derivatives. And so you're talking about stress or strain. Even in heat transfer, you're talking about things like heat flux or heat transfer rate. All of those depend on the derivative of the solution, right? And so when you have constant derivatives, at least constant derivatives within your element, that can lead to derived quantities that are not as accurate as they should. Now, what's unique about the linear quadrilateral is that it kind of gets around this a little bit because of that pseudo-linear term. And so when you take the derivative of that pseudo-linear term, you still get something that depends, that has some variable dependence. And so, you take the derivative with respect to x, you get a1 plus a3y. You take the derivative with respect to y, you get a2 plus a3x. And having that dependence, even though it's very weak, it's only in one variable, actually can make a really big difference sometimes. And so if you remember last time we talked about the mesh, we talked about this idea or this problem called shear locking. And so shear locking, basically what happens with shear locking is that, shear locking occurs is because when you have elements that have constant stress throughout, and having constant stress elements is a key or kind of a property of linear triangles, it can cause the element to kind of lock up because you don't have a gradient of stress that's there to cause, the deformations or internal deformations. So that's why, we discuss when you're using ANSYS and you have the ability to kind of very easily kind of switch between linear and quadratic elements, there's really no reason to use linear elements for, for anything that we're doing in this class, or just anything that you're using in ANSYS in general, unless you're doing a thermal simulation or a fluid mechanics simulation. Most of the time, it's just easier and better just to use quadratic. Because then, your solution quality is going to be a lot better. We're going to discuss the quadratic elements after this, and you avoid this idea, or you avoid this problem of shear locking because the stress is not going to be constant within your. All right, any questions on this before we start talking about the quadratic elements? Okay, all right, so let's look at the quadratic elements and let's see what their shape functions look like. So let's start with a triangle. Okay. So the quadratic triangular element, the element is still going to be a triangle, but now our shape function is going to be of quadratic form. Okay, so let's draw the triangle once again. Triangle, 3 nodes, 1, 2, 3. Okay. Okay, so our shape function now is going to be quadratic. But remember, whenever we form a shape function and it's going to go up to a certain order, we have to include all the lower order terms as well. So that means all the linear terms are going to be there too, but we're going to add additional terms to our shape function until we get a quadratic function. Okay, so let's write out our shape function here. So we have p of x, y. So remember, we're adding terms to our linear shape function. So we have to include everything that was there before. We have a0 plus a1x plus a2y. Okay. So that's just a requirement of all FEA shape functions. And so if you're curious, it's called the completeness property. And so for your element to be complete, it has to include all the lower order terms in the polynomial as well. Okay. There's a mathematical reason and a proof to that, but of course, we're not going through that. Here, you can look it up. Okay. All right, so we're gonna add some additional terms here, but we're kind of stuck a little bit, right? Because remember, one thing we discussed earlier is that the number of terms in your shape function has to match the number of nodes in the element itself, right? But our element here is 3 nodes, right? It's a triangle. And so, we can't, right now, we can't really add any more terms to our shape function because our element itself only has 3 nodes, okay? So how can we get a polynomial that's quadratic, but also still matches the same number of nodes in our element, right? The only solution to this is for us to add some additional nodes to the element itself. Okay. And so the nodes that we're going to add here are actually going to be right in the middles of each of the edges. Okay, so we're going to add one node between nodes 1 and 2. So we'll call this node 4. We're going to add a node between nodes 2 and 3. We'll call this node 5. And we're going to add one node here between nodes 1 and 3. So we'll call that node 6. Okay. So nodes 4, 5, and 6 here, we call them a special name because they're not located at the vertices of the element. We call these mid nodes. Because they are nodes that occur in the middle of each of the edges. Okay. So these still satisfy the properties of nodes, and so because they're on the edges of the element, these nodes are still shared between multiple elements. The thing with mid nodes is that they're only shared between 2 elements because they're only on an edge, or at least in 2D. And so the number of elements that share these mid nodes is less than the regular nodes. The number of neighboring elements. So the mid nodes, those are the nodes that occur at the middles of the edges. And so for a 2D mesh, there's only going to be 2 elements that share those mid nodes. The other nodes, the nodes 1, 2, and 3, I call those vertex nodes because those are at the vertices of the element itself. Okay. It's a small distinction. Honestly, for what we're going to discuss, it doesn't make too much difference because at the end of the day, a node is a node, and you still have to match the solution with the nodes, whether they're a vertex node or a mid node. But they are kind of strangely placed, and so I did want to make that distinction. Okay, but in terms of our shape function, that means we have 3 additional terms that we can play with, 3 additional terms that we can add, and this is what's going to allow us to add those quadratic order terms. Okay. Okay, so let's add three terms here. So we're going to add A3. So the first one we're going to add is that pseudo linear term that was present in our linear quadrilateral. So this is A3xy. Next, we have the straight up quadratic term. So this is going to be A4 x squared and A5 y squared. Okay, so that's our shape function for the quadratic triangle. So you can see it has double the amount of terms as our linear triangle. And so it's going to give you a much higher quality solution. It's even, it's even better than the linear quadrilateral as well, because you have that x squared and y squared, right? And those quadratic terms are actually really nice because if you have solutions or if you have an approximate solution that's going to change values very rapidly, which can occur in structural mechanics as well. So you have stresses or deformation that change very quickly over a short period of, over short space. Then those quadratic terms are going to be able to capture that behavior much more accurately. Of course, this extra solution quality doesn't come free. Adding those extra nodes there does increase the computational cost. That's usually the case, and so when you want more accuracy, usually that comes with an increase in cost. So increasing the element order also is no different than that. But usually it's worth it, especially for a software like ANSYS where it makes it so easy to change the element order. You might as well just pick quadratic, because and a lot of times you're not really going to notice the difference in cost. Most of the times the difference in cost is only noticeable if you have meshes with over 1 million elements or something like that, which we're not really going to get into that regime. Okay. Any questions on the quadratic triangular elements? Okay, all right. So last element type that we're going to go over today is the quadratic quadrilateral. Tongue twister, quadratic quadrilateral, quadratic quadrilateral. Okay. You can only say it twice. Okay. Let me go ahead and draw that quadrilateral element. The quadrilateral element looks like this. It has 4 vertices. So let's label those first. So we have vertex 1, 2, 3, vertex 4. If we learn from our experience from the quadratic triangle, that means we know that we're going to add mid nodes. And so between every 2 vertex nodes there, we're going to add an additional node. Okay. So there's going to be node 5, 6, 7, and 8. Oh, you mean that node 7 is not in the middle. We have 8 nodes to play with, and so that means our shape function is going to have 8 terms in its expression. Okay, so our shape function is its own line because it's going to be long. Okay. Okay. So we start with the linear terms, and so we have a0 plus a1x plus a2y. Okay. Let's add the pseudo-linear term as well, because that was part of our linear quadrilateral before. We have a3 xy. Let's add the straight up quadratic terms. A4 squared plus a5 squared. Okay. So that's 6 terms. These are all the terms that were inside our quadratic triangle. But we need 2 more terms, right? Because our element here has 8 nodes in total. So that means we have 8 terms in our shape function. Okay. So we're going to cheat a little bit too here, just like we did with the linear quadrilateral. So we're going to add terms that are technically speaking not quadratic, but they're pseudo quadratic, and that means they're quadratic in one of the directions, but not the other. Okay. Okay. So we're going to add a6 x squared y plus A7 y squared x. Okay, so that's our shape function for our quadratic quadrilateral. Okay. If you wanted to solve for the values for all the constants, A0 through A7, then again, you can set up a system of equations. In this case, it's an 8x8 system, so 8 equations, 8 unknowns. So that's something, practically speaking, you're not going to solve by hand, but that's something that the computer can do. Right? And when you compare this to the quadratic triangle, because we have additional terms here, that means our solution is going to be higher quality. So the main place where the quadratic quadrilateral kind of excels over the triangle is in its derivatives. Okay. And so when you take the derivative of this, because we have these kind of pseudo quadratic terms, right? So because we have this A6 and A7, right? When you take the derivative of this function, you're still going to get some quadratic terms in the expression. So let's say you take the derivative of the shape function here with respect to y, then you're still gonna have an a6 x squared there, right? Or you take the derivative with respect to, well, let's say you take the derivative with respect to y, then your a7 term is gonna be a7 times 2y times x, right? And so when you have derivative quantities like stresses or strains that are going to vary rapidly with x or y, then those extra terms there are going to be very, very valuable. And ultimately, that's kind of the motivation of using quadratic elements. It's because you have those quadratic terms, anything that changes more rapidly, so it has kind of a quadratic dependence rather than linear dependence, you're going to capture that behavior much, much better. And that goes for multiple things too. So, solution quality, I think, is the main one that people will think about, but it also changes how you model the geometry itself. Some of you may have noticed this in our ANSYS activities so far, but if you use a fairly coarse mesh, your geometry kind of gets messed up a little bit, and so it kind of becomes pixelated. And so the element order actually helps with that as well. So if you have kind of a very coarse mesh, having a quadratic element means that your elements are going to be, a little bit more closer to the original geometry. It may not show that in ANSYS because ANSYS kind of renders the elements all as linear. But quadratic elements actually do change how you model the geometry, which can be helpful. Okay. All right, any questions on this? Okay, all right, so we'll end a bit early today. So we'll pick this up again next Tuesday. So next Tuesday, we're going to be talking about the 3D elements. And so all the 3D counterparts of these elements here. So we'll take a look at their shape functions and we'll see how this interaction kind of changes things. But before that, on Thursday, we have our next ANSYS activity. So ANSYS activity solution. Okay. So thank you guys for coming today. I hope you guys have a good rest of your evening, and I will see you all on Thursday.
No, I think it's only.
I can't even.
That's all I got. Oh, I saw that.
Another one. Oh, the fight.
Yeah. Video. One of those.
Okay. Okay. So what do you mean by smart? Yeah. I was Mike's. It doesn't. Started the flow. Yeah, first time you do it, there's weird stuff that happens. Okay, yeah, I mean, if there's any, if there's, not too much to update, we can probably skip it this week. If you're having issues, just email me, then we can discuss. Okay.
Today.
Okay. Alright.
Other times that you said it.